Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on heat exchangers in plants which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the basic principles of fluid flow inside a heat exchanger. Explain the methods of heat transfer that apply to heat exchangers. Compare the operation of finned and plain tubes. List the basic parts of a hairpin, double pipe, heat exchanger. Describe a shell end tube, fixed head, and single pass heat exchanger. Describe a shell end tube, fixed head, and multi-pass heat exchanger. Describe a U-tube heat exchanger. Describe the operating principles of a kettle and thermosiphon reboiler. Describe the types of heat exchangers used on a distillation tower. Draw a simple heat exchanger system. Describe the basic components and operation of a plate and frame heat exchanger. Identify the basic components of an air-cooled heat exchanger. Explain the operation and design of a spiral heat exchanger. Respond to problems associated with heat exchangers. Before starting the course, let us have a look at key terms. Baffles are evenly spaced partitions in a shell end tube heat exchanger that support the tubes, prevent vibration, control fluid velocity and direction, increase turbulent flow, and reduce hotspots. Channel head is a device mounted on the inlet side of a shell end tube heat exchanger that is used to channel tube side flow in a multi-pass heat exchanger. Condenser is a shell end tube heat exchanger used to cool and condense hot vapors. Conduction is the means of heat transfer through a solid, non-porous material resulting from molecular vibration. Conduction can also occur between closely packed molecules. Convection is the means of heat transfer in fluids resulting from currents. Counterflow refers to the movement of two flow streams in opposite directions, also called countercurrent flow. Crossflow refers to the movement of two flow streams perpendicular to each other. Differential pressure is the difference between inlet and outlet pressures, represented as delta P or delta P. Differential temperature is the difference between inlet and outlet temperature, represented as delta T. Fixed head is a term applied to a shell end tube heat exchanger that has the tube sheet firmly attached to the shell. Floating head is a term applied to a tube sheet on a heat exchanger that is not firmly attached to the shell on the return head and is designed to expand or float inside the shell as temperature rises. Fouling is buildup on the internal surfaces of devices such as cooling towers and heat exchangers, resulting in reduced heat transfer and plugging. Kettle reboiler is a shell end tube heat exchanger with a vapor disengaging cavity, used to supply heat for separation of lighter and heavier components in a distillation system and to maintain heat balance. Laminar flow is streamlined flow that is more or less unbroken, layers of liquid flowing in a parallel path. Multi-pass heat exchanger is a type of shell end tube heat exchanger that channels the tube side flow across the tube bundle or heating source more than once. Parallel flow refers to the movement of two flow streams in the same direction, for example, tube side flow and shell side flow in a heat exchanger, also called concurrent. Radiant heat transfer is conveyance of heat by electromagnetic waves from a source to receivers. Reboiler is a heat exchanger used to add heat to a liquid that was once boiling until the liquid boils again. Sensible heat is heat that can be measured or sensed by a change in temperature. Shell end tube heat exchanger is a heat exchanger that has a cylindrical shell surrounding a tube bundle. Shell side refers to flow around the outside of the tubes of a shell end tube heat exchanger. Thermosiphon reboiler is a type of heat exchanger that generates natural circulation as a static liquid is heated to its boiling point. Tube sheet is a flat plate to which the ends of the tubes in a heat exchanger are fixed by rolling, welding, or both. Tube side refers to flow through the tubes of a shell end tube heat exchanger. Turbulent flow is random movement or mixing in swirls and eddies of a fluid. Types of heat exchangers. Heat transfer is an important function of many industrial processes. Heat exchangers are widely used to transfer heat from one process to another. A heat exchanger allows a hot fluid to transfer heat energy to a cooler fluid through conduction and convection. A heat exchanger provides heating or cooling to a process. A wide array of heat exchangers has been designed and manufactured for use in the chemical processing industry. In pipe coil exchangers, pipe coils are submerged in water or sprayed with water to transfer heat. This type of operation has a low heat transfer coefficient and requires a lot of space. It is best suited for condensing vapors with low heat loads. The double pipe heat exchanger incorporates a tube within a tube design. It can be found with plain or externally thin tubes. Double pipe heat exchangers are typically used in series flow operations in high pressure applications up to 500 psi shell side and 5000 psi tube side. A shell end tube heat exchanger has a cylindrical shell that surrounds a tube bundle. Fluid flow through the exchanger is referred to as tube side flow or shell side flow. A series of baffles support the tubes, direct fluid flow, increase velocity, decrease tube vibration, protect tubing, and create pressure drops. Shell end tube heat exchangers can be classified as fixed head, single pass, fixed head, multi-pass, floating head, multi-pass, or U-tube. On a fixed head heat exchanger as shown in picture, tube sheets are attached to the shell. Fixed head heat exchangers are designed to handle temperature differentials up to 200 degrees Fahrenheit or 93.33 degrees Celsius. Thermal expansion prevents a fixed head heat exchanger from exceeding this differential temperature. It is best suited for condenser or heater operations. Floating head heat exchangers are designed for high temperature differentials above 200 degrees Fahrenheit or 93.33 degrees Celsius. During operation, one tube sheet is fixed and the other floats inside the shell. The floating end is not attached to the shell and is free to expand. Reboilers are heat exchangers that are used to add heat to a liquid that was once boiling until the liquid boils again. Types commonly used in industry are kettle reboilers and thermosiphon reboilers. Plate and frame heat exchangers are composed of thin, alternating metal plates that are designed for hot and cold service. Each plate has an outer gasket that seals each compartment. Plate and frame heat exchangers have a cold and hot fluid inlet and outlet. Cold and hot fluid headers are formed inside the plate pack, allowing access from every other plate on the hot and cold sides. This device is best suited for viscous or corrosive fluid slurries. It provides excellent high heat transfer. Plate and frame heat exchangers are compact and easy to clean. Operating limits of 350 degrees Fahrenheit to 500 degrees Fahrenheit or 176.66 degrees Celsius to 260 degrees Celsius are designed to protect the internal gasket. Because of the design specification, plate and frame heat exchangers are not suited for boiling and condensing. Most industrial processes use this design in liquid-liquid service. Air-cooled heat exchangers do not require the use of a shell in operation. Process tubes are connected to an inlet and a return header box. The tubes can be finned or plain. A fan is used to push or pull outside air over the exposed tubes. Air-cooled heat exchangers are primarily used in condensing operations where a high level of heat transfer is required. Spiral heat exchangers are characterized by a compact concentric design that generates high fluid turbulence in the process medium. As do other exchangers, the spiral heat exchanger has cold medium inlet and outlet and a hot medium inlet and outlet. Internal surface area provides the conductive transfer element. Spiral heat exchangers have two internal chambers. The Tubular Exchanger Manufacturers Association, TEMA, classifies heat exchangers by a variety of design specifications including American Society of Mechanical Engineers, ASME, Construction Code, Tolerances, and Mechanical Design. Class B, designed for general purpose operation, economy and compact design. Class C, designed for moderate service and general purpose operation, economy and compact design. Class R, designed for severe conditions, safety and durability. Heat transfer and fluid flow. The methods of heat transfer are conduction, convection, and radiant heat transfer as shown in picture. In the petrochemical, refinery, and laboratory environments, these methods need to be understood well. A combination of conduction and convection heat transfer processes can be found in all heat exchangers. The best conditions for heat transfer are large temperature differences between the products being heated and cooled. The higher the temperature difference, the greater the heat transfer, high heating or coolant flow rates, and a large cross-sectional area of the exchanger. Conduction. Heat energy is transferred through solid objects such as tubes, heads, baffles, plates, fins, and shell by conduction. This process occurs when the molecules that make up the solid matrix begin to absorb heat energy from a hotter source. Since the molecules are in a fixed matrix and cannot move, they begin to vibrate and, in so doing, transfer the energy from the hot side to the cooler side. Convection. Convection occurs in fluids when warmer molecules move toward cooler molecules. The movement of the molecules sets up currents in the fluid that redistribute heat energy. This process will continue until the energy is distributed equally. In a heat exchanger, this process occurs in the moving fluid media as they pass by each other in the exchanger. Baffle arrangements and flow direction will determine how this convective process will occur in the various sections of the exchanger. Radiant heat transfer. The best example of radiant heat is the sun's warming of the Earth. The sun's heat is conveyed by electromagnetic waves. Radiant heat transfer is a line-of-sight process, so the position of the source and that of the receiver are important. Radiant heat transfer is not used in a heat exchanger. Laminar and turbulent flow. Two major classifications of fluid flow are laminar and turbulent as shown in picture. Laminar or streamlined flow moves through a system in thin cylindrical layers of liquid flowing in parallel fashion. This type of flow will have little, if any, turbulence, swirling or eddying in it. Laminar flow usually exists at low flow rates. As flow rates increase, the laminar flow pattern changes into a turbulent flow pattern. Turbulent flow is the random movement or mixing of fluids. Once the turbulent flow is initiated, molecular activity speeds up until the fluid is uniformly turbulent. Turbulent flow allows molecules of fluid to mix and absorb heat more readily than does laminar flow. Laminar flow promotes the development of static film, which acts as an insulator. Turbulent flow decreases the thickness of static film, increasing the rate of heat transfer. Parallel and series. Flow heat exchangers can be connected in a variety of ways. The two most common are series and parallel as shown in picture. In series flow as shown in picture, the tube side flow in a multi-pass heat exchanger is discharged into the tube side flow of the second exchanger. This discharge route could be switched to shell side or tube side depending on how the exchanger is in service. The guiding principle is that the flow passes through one exchanger before it goes to another. In parallel flow, the process flow goes through multiple exchangers at the same time. Heat exchanger effectiveness and common problems. The design of an exchanger usually dictates how effectively it can transfer heat energy. Fouling is one problem that stops an exchanger's ability to transfer heat. During continual service, heat exchangers do not remain clean. Dirt, scale, and process deposits combine with heat to form restrictions inside an exchanger. These deposits on the walls of the exchanger resist the flow that tends to remove heat and stop heat conduction by insulating the inner walls. An exchanger's fouling resistance depends on the type of fluid being handled, the amount and type of suspended solids in the system, the exchanger's susceptibility to thermal decomposition, and the velocity and temperature of the fluid stream. Fouling can be reduced by increasing fluid velocity and lowering the temperature. Fouling is often tracked and identified using checklists that collect tube inlet and outlet pressures and shell inlet and outlet pressures. This data can be used to calculate the pressure differential or delta P. Differential pressure is the difference between inlet and outlet pressures, represented as delta P, or delta P. Corrosion and erosion are other problems found in exchangers. Chemical products, heat, fluid flow, and time tend to wear down the inner components of an exchanger. Chemical inhibitors are added to avoid corrosion and fouling. These inhibitors are designed to minimize corrosion, algae growth, and mineral deposits. Other problems associated with heat exchangers include internal or external tube leaks, gasket leaks, tube sheet leakage, damaged or crushed tubes, air-cooled fins that are crushed or fouled, decreased flows due to poor pump performance, sheared tubes, or air trapped in the shell. A heat exchanger's effectiveness is typically linked to three things. First, flow rate of each process stream. Second, temperature differences between the two opposing streams. And third, the cross-sectional area of the heat exchanger. Double pipe heat exchanger. A simple design for heat transfer is found in a double pipe heat exchanger. A double pipe exchanger has a pipe inside a pipe as shown in picture. The outside pipe provides the shell, and the inner pipe provides the tube. The warm and cool fluids can run in the same direction, parallel flow, or in opposite directions, counterflow or countercurrent. Flow direction is usually countercurrent because it is more efficient. This efficiency comes from the turbulent, against the grain, stripping effect of the opposing currents. Even though the two liquid streams never come into physical contact with each other, the two heat energy streams, cold and hot, do encounter each other. Energy-laced, convective currents mix within each pipe, distributing the heat. In a parallel flow exchanger, the exit temperature of one fluid can only approach the exit temperature of the other fluid. In a countercurrent flow exchanger, the exit temperature of one fluid can approach the inlet temperature of the other fluid. Less heat will be transferred in a parallel flow exchanger because of this reduction in temperature difference. Static films produced against the piping limit heat transfer by acting like insulating barriers. The liquid close to the pipe is hot, and the liquid farthest away from the pipe is cooler. Any type of turbulent effect would tend to break up the static film and transfer heat energy by swirling it around the chamber. Parallel flow is not conducive to the creation of turbulent eddies. One of the system limitations of double pipe heat exchangers is the flow rate they can handle. Typically, flow rates are very low in a double pipe heat exchanger, and low flow rates are conducive to laminar flow. Hairpin heat exchangers. The chemical processing industry commonly uses hairpin heat exchangers as shown in picture. Hairpin exchangers use two basic modes, double pipe and multi-pipe design. Hairpins are typically rated at 500 psig shell side and 5000 psig tube side. The exchanger takes its name from its unusual hairpin shape. The double pipe design consists of a pipe within a pipe. Fins can be added to the internal tube's external wall to increase heat transfer. The multi-pipe hairpin resembles a typical shell end tube heat exchanger, stretched and bent into a hairpin. The hairpin design has several advantages and disadvantages. Among its advantages are its excellent capacity for thermal expansion because of its U-tube type shape, its fin design, which works well with fluids that have a low heat transfer coefficient, and its high pressure on the tube side. In addition, it is easy to install and clean, its modular design makes it easy to add new sections, and replacement parts are inexpensive and always in supply. Among its disadvantages are the facts that it is not as cost-effective as most shell end tube exchangers and it requires special gaskets. Shell end tube heat exchangers. The shell end tube heat exchanger is the most common style found in industry. Shell end tube heat exchangers are designed to handle high flow rates in continuous operations. Tube arrangement can vary depending on the process and the amount of heat transfer required. As the tube side flow enters the exchanger or head flow is directed into tubes that run parallel to each other. These tubes run through a shell that has a fluid passing through it. Heat energy is transferred through the tube wall into the cooler fluid. Heat transfer occurs primarily through conduction, first, and convection, second. This picture shows a fixed head, single-pass heat exchanger. Fluid flow into and out of the heat exchanger is designed for specific liquid vapor services. Liquids move from the bottom of the device to the top to remove or reduce trapped vapor in the system. Gases move from top to bottom to remove trapped or accumulated liquids. This standard applies to both tube side and shell side flow. Designs and components. Exchanger nomenclature uses the terms front end, shell or middle section, and rear end to refer to the three parts of shell and tube heat exchangers. The front-end design of a heat exchanger varies depending on the type of service in which it will be used. The shell has 7 popular designs that are linked to the way flow moves through the shell. The rear-end section of a heat exchanger is linked to the front-end design. Industrial manufacturers are currently using over 9 popular designs. Head. The heads as shown in picture on a shell and tube heat exchanger can be classified as front-end or rear-end types. The front-end head has 5 primary designs. 1. Channel and removable cover. 2. Bonnet. 3. Channel integral with the tube sheet and removable cover, removable tube bundle. 4. Channel integral with the tube sheet and removable cover, fixed to shell. And 5. Special high-pressure closure. The rear end, or return, header has 8 possible designs. 1. Fixed tube sheet with channel and removable cover. 2. Fixed tube sheet with bonnet. 3. Channel integral with the tube sheet and removable cover, fixed to shell. 4. Outside packed floating head. 5. Floating head with backing device. 6. Pull-through floating device. 7. U-tube bundle. And 8. Externally sealed floating tube sheet. Shell. The shell can be classified as single pass, double pass, split flow, double split flow, divided flow, kettle, or cross flow as shown in picture. The shell is designed to operate at a specific temperature and pressure, which are clearly marked on the manufacturer's code stamp plate. Process technicians can determine the type of shell flow by the positions of the inlet and outlet ports. The shell is the largest single part of the heat exchanger, but if the cross-sectional surface area of the tubes were calculated and compared with the surface area of the shell would look very small. In most cases, the shell is designed to withstand the greatest temperature and pressure conditions. The shell has inlet and outlet nozzles. The total number and placement of nozzles will depend on the design. Tubes. Tubes on shell and tube heat exchangers can be plain or finned as shown in picture. Fins provide more surface area and allow greater heat transfer to take place. Fins can be located externally or internally. Although plain tubes are more commonly used in fabrication, the enhanced features of the fin tube are starting to make an impact on new design engineers. Tube materials include brass, carbon steel, copper, cupronickel, glass, stainless steel, specialty alloys, Monel, nickel, and tantalum. Tube sheet. Tube sheets are often described as fixed or floating, single or double. A tube sheet is a flat plate to which the ends of the tubes in a heat exchanger are fixed by rolling, welding, or both. Tube sheets have carefully drilled holes designed to admit the end of a tube and secure it to the plate. Double tube sheets are used to prevent tube side leakage of highly corrosive fluids. The space between the plates provides a void where these hazardous materials can be safely removed from the process stream. Tube sheet connections are identified as plain, rolled, beaded or belled, flared, or welded as shown in picture. Some connections are both rolled and welded. A duplex tube inside a tube, can be beaded or belled, plain or flared. During operation, the tubes will expand. This expansion creates a problem within a fixed head design. Engineering specifications take into account thermal tube expansion. The term fixed tube sheet applies to the way the tube sheet is located in the inlet or return head. If the tube sheet is welded or bolted to the shell, it is fixed. If the tube sheet is independently secured to the tub head and is allowed to move freely inside the shell, it is floating. Baffles. Internal baffles are structurally important to the performance of a shell and tube heat exchanger. Baffles provide the framework to support and secure the tubes and prevent vibration. The baffle layout increases or decreases fluid and directs flow at specific points. Tube-side baffles, or pass partitions, are built into the heads to direct tube-side flow. Tube-side baffles may be cast or welded in place. Single-pass exchangers do not need a baffle in the inlet or return head. Multi-pass exchangers requiring 2 passes will have a single baffle in the inlet channel head. A variety of baffle arrangements are available. Cost goes up with each pass. Additional passes are often needed to provide adequate fluid velocities to prevent fouling, internal buildup of material, and to control heat transfer. Segmental baffles, as shown in picture, are often used in horizontal shell and tube heat exchangers. The holes in the baffle are drilled to fit the size of the tube. Without support, tubes will vibrate under pressure. Each segmental baffle supports half of the tubes. Baffles are evenly spaced and alternated from one side to the other to support the tube bundle and direct fluid flow. Segmental baffles may be horizontal or vertical cut. The choice of which arrangement to use is based on the required service. For example, a vertical arrangement is typically used in horizontal exchangers used as condensers, reboilers, or vaporizers. Systems transferring large quantities of suspended solids may also use this design. The vertical design allows liquid and solids to flow around baffles. Horizontal baffles are used in vapor phase or all liquid phase operations. This type of arrangement is not used where entrained gases are trapped in the liquid unless V-notches are cut in the bottom of the baffle. Horizontal baffles are used in clean service with notches at the bottom to allow liquid drainage on removal from service. Impingement baffles are used to protect tubing from direct fluid impact. In some systems, high-pressure steam is admitted into the shell side. An impingement baffle, placed over the tubes, will deflect the steam as it enters the exchanger, thereby preventing cutting, pitting, and erosion problems in the tubes. Longitudinal baffles are used inside the shell to split or divide the flow, increase velocity, and provide superior heat transfer capabilities. This type of baffle can be welded in place, slid into a slot, or situated with special packing. Longitudinal baffles do not extend the entire length of the exchanger because at some point the fluid must flow around it. Tie rods. Tie rods and concentric tube spacers keep the baffles in place and evenly spaced. Each hole in the baffle plates is 1/64 inch larger than the tube's outside diameter. Tube vibrations on the leading edge of the baffle will eventually damage the tube. Tie rods hold the baffles in place and prevent vibration and excessive tube movement. Nozzles and accessory parts. Shell and tube inlet and outlet nozzles are sized for pressure drop and velocity considerations. Nozzle connections frequently have thermos wells, a chamber that houses temperature sensing devices, and pressure indicator connections. Safety and relief valves are located in required areas around the exchanger. Product drains are used to empty the sections between baffles during maintenance. Vents are located on the upper side of the shell to remove gases and vapors. Block valves and control valves are located in the piping entering and leaving the exchanger. Fixed head, single pass. The term fixed head refers to the physical connection between the tube sheet and tubes in the head. In a fixed head, single-pass shell and tube heat exchanger, the tubes are connected to 2 tube sheets that are firmly attached to the shell, and 2 stationary heads as shown in picture. Process flow, tube inlet, enters the head and is directed toward the fixed tube sheets. Each tube sheet is a flat, metal disc that functions like a collar for the individual tubes. The tube sheets can be hollow or solid. The hollow design is for leakage protection. As flow enters the tubes, it experiences maximum heat transfer. Conductive heat transfer is at its highest where the tube sheet, shell, and tubes meet. By the time the tube flow exits the exchanger, very little, if any, heat transfer is taking place. The term single pass indicates that the tube side flow goes across the exchanger one time. Fixed head, multi-pass. A fixed head, multi-pass shell and tube heat exchanger is designed much like the single-pass exchanger. The differences occur with the number of passes the tube side flow takes across the exchanger, the baffle or pass partition added to the channel head, and the lack of a tube side outlet on the discharge head as shown in picture. In a fixed head, multi-pass heat exchanger, flow enters the channel head and is directed into the tubes. A baffle installed in the head limits access to a portion of tubes on the tube sheet. As fluid flows through the exchanger, heat is transferred into or out of the fluid. After completing the first pass, process flow is directed back into another portion of tubes. This second pass across the exchanger allows additional heat transfer to occur. As tube side flow moves through the exchanger, it encounters a variety of flow variations from the shell side. Since heat transfer in a shell and tube exchanger occurs primarily through conduction and convection, the hotter fluid will influence the cooler. At various points, the tube and shell flows run parallel, that is, as counterflow, which is also called crossflow. Baffle arrangement influences the directions heat transfer and fluid flow take. The basic heat transfer relation is Q equals UA, where Q is the heat duty, in BTU per hour, U is the overall heat transfer coefficient, in BTU per hour per square foot of surface, and A is the area available for heat transfer, in square feet. Counterflow operation provides more heat transfer than parallel flow. Floating head. In a floating head, multi-pass shell and tube heat exchanger, one side of the tube bundle is fixed to the channel head, the other side is unsecured, or floating as shown in picture. Flow enters the channel head and is directed into the tubes that are attached to a common, fixed, tube sheet. As flow moves from left to right, it makes one pass before it crosses right to left for the second pass. A network of baffles is established on the tube bundle to enhance heat transfer. Adding fins to the tubes can further enhance heat transfer. An impingement baffle or pass partition is located between the tubes and shell inlet. This redirects the flow and keeps the tubes from being damaged. This type of heat exchange produces the highest heat transfer efficiency. Floating head exchangers, with their high cross-sectional areas or fins, are designed for high temperature differentials and high flow rates. U-tube. A fixed tube sheet on one end that is typically bolted to the shell characterizes a U-tube exchanger as shown in picture. The tube sheet connects a series of tubes bent in a U shape as shown in picture. The ends of the tubes are secured to the tube sheet. This design limits the total number of tubes that can be used when compared with a fixed head. A channel head directs tube flow across the body of the exchanger twice. U-tube exchangers are specially designed for large temperature differentials. The U-shaped design allows the head to float and accommodate the thermal expansion of the tubes. Each complete U-tube has a single fundamental frequency as flow passes over it. Segmental baffles placed at equal distances provide the support and framework that bond the tubular bundle into a single unit. Longitudinal baffles may be used to direct fluid flow. Reboilers. Reboilers are used to add heat to a liquid that was once boiling until the liquid boils again. Reboilers are closely associated with the operation of a distillation column. Typical reboiler arrangements include 5 basic patterns: flooded tube kettle reboiler, natural circulation, forced circulation, vertical thermosiphon, and horizontal thermosiphon as shown in picture. These types of devices are classified by how they produce fluid flow. If a mechanical device, such as a pump, is used, the reboiler is referred to as a forced circulation reboiler. Circulation that does not require a pump is classified as natural circulation. Kettle reboiler. Kettle reboilers are shell and tube heat exchangers designed to produce a two-phase, vapor-liquid mixture that can be returned to a distillation column as shown in picture. Kettle reboilers have a removable tube bundle that uses steam or a high-temperature process medium to boil the fluid. A large vapor cavity above the heated process medium allows vapors to concentrate. Liquid that does not vaporize flows over a weir and into the liquid outlet. Hot vapors are sent back to the distillation column through the reboiler's vapor outlet ports. This process controls the level in the bottom of the distillation column, maintains product purity, strips smaller hydrocarbons from larger ones, and helps maintain the critical energy balance on the column. Kettle reboilers operate with liquid levels from 2 inches above and 2 inches below the upper tubes. Engineering designs typically allow 10 inches to 12 inches of vapor space above the tube bundle. Vapor velocity exiting the reboiler must be low enough to prevent liquid entrainment. Bottom product spills over the weir that fixes the liquid level on the tube bundle. An important concept with a distillation column is energy or heat balance. Reboilers are used to restore this balance by adding additional heat for the separation processes. Bottom products typically contain the heavier components from the tower. Reboilers take suction off of the bottom products and pump them through their system. Column temperatures are controlled at established set points. Product flow enters the bottom shell side of a reboiler. As flow enters the reboiler, it comes into contact with the tube bundle. The tubes have steam or hot fluids flowing through them. As the bottom product comes into contact with the tubes, a portion of the liquid is flashed off or vaporized and captured in the dome-shaped vapor cavity at the top of the reboiler shell. This vapor is sent back to the tower for further separation. A weir contains the unflashed portion of the liquid in a reboiler. Excess flow goes over the weir and is recirculated through the system. Kettle reboilers are easy to control because circulation and two-phase flow rates are not considerations. Vertical and horizontal thermosiphon reboilers. A thermosiphon reboiler is a fixed-head, single-pass heat exchanger connected to the side of a distillation column. Thermosiphon heat exchangers can be mounted vertically or horizontally. The critical design factor is providing sufficient liquid head in the column to support vapor or liquid flowback to the column. Natural circulation occurs because of the differences in density between the hotter liquid in the reboiler and the liquid in the distillation tower. One side of the exchanger is used for heating, usually with steam or hot oil. The other side takes suction off the column. When steam is used as the heated medium in a vertical exchanger, it enters from the top shell inlet and flows downward to the shell outlet to allow for the removal of condensate. The lower tube inlet of the exchanger usually takes suction at a point low enough on the column to provide a liquid level to the exchanger. A pump is not connected to the column and exchanger unless a forced circulation system is required. This system uses buoyancy forces to flash off and pull in liquid. Newton's third law of motion, which states that for every action there is an equal and opposite reaction, is a basic operating principle of thermosiphon reboilers. As liquids and vapors circulate back to the column, the inlet line provides fresh liquid to support the circulation. Stab-in reboiler. The stab-in reboiler is mounted directly into the base of the distillation column. Steam or hot oil is used as the heating medium. Heat energy is transferred directly into the process medium. The lower section on a distillation column is specially designed to allow the bottom product to boil. This lower section maintains a liquid seal as hot vapors move up the column and heavy liquids collect in the bottom. Hot oil jacket reboiler. Some reboilers have specially designed hot oil jackets surrounding the bottom of the column. In this type of service, hot oil enters the outer shell and provides heat to the bottom product primarily through conduction and convection. The outer jacket functions like a heat exchanger as hot fluid circulates through the shell. This type of system is used on smaller distillation systems. Plate and frame heat exchangers. Plate and frame heat exchangers are high heat transfer and high pressure drop devices. They consist of a series of gasket plates, sandwiched together by two end plates and compression bolts as shown in pictures. The channels between the plates are designed to create pressure drop and turbulent flow so high heat transfer coefficients can be achieved. The openings on the plate exchanger are located typically on one of the fixed end covers. As hot fluid enters the hot inlet port on the fixed end cover, it is directed into alternating plate sections by a common discharge header. The header runs the entire length of the upper plates. As cold fluid enters the countercurrent cold inlet port on the fixed end cover, it is directed into alternating plate sections. Cold fluid moves up the plates while hot fluid drops down across the plates. The thin plates separate the hot and cold liquids, preventing leakage. Fluid flow passes across the plates one time before entering the collection header. The plates are designed with an alternating series of chambers. Heat energy is transferred through the walls of the plates by conduction and into the liquid by convection. The hot and cold inlet lines run the entire length of the plate heater and function like a distribution header. The hot and cold collection headers run parallel and on the opposite side of the plates from each other. The hot fluid header that passes through the gasket plate heat exchanger is located at the top. This arrangement accounts for the pressure drop and turbulent flow as fluid drops over the plates and into the collection header. Cold fluid enters the bottom of the gasket plate heat exchanger and travels countercurrent to the hot fluid. The cold fluid collection header is located in the upper section of the exchanger. Plate and frame heat exchangers have several advantages and disadvantages. They are easy to disassemble and clean and distribute heat evenly so there are no hot spots. Plates can easily be added or removed. Other advantages of plate and frame heat exchangers are their low fluid resistance time, low fouling, and high heat transfer coefficient. In addition, if gaskets leak, they leak to the outside, and gaskets are easy to replace. The plates prevent cross-contamination of products. Plate and frame heat exchangers provide high turbulence and a large pressure drop and are small compared with shell end tube heat exchangers. Disadvantages of plate and frame heat exchangers are that they have high pressure and high temperature limitations. Gaskets are easily damaged and may not be compatible with process fluids. Spiral heat exchangers. Spiral heat exchangers are characterized by a compact concentric design that generates high fluid turbulence in the process medium as shown in picture. This type of heat exchanger comes in two basic types: 1. Spiral flow on both sides, and 2. Spiral flow cross-flow. Type 1 spiral exchangers are used in liquid-liquid, condenser, and gas cooler service. Fluid flow into the exchanger is designed for full counterflow operation. The horizontal axial installation provides excellent self-cleaning of suspended solids. Type 2 spiral heat exchangers are designed for use as condensers, gas coolers, heaters, and reboilers. The vertical installation makes it an excellent choice for combining high liquid velocity and low pressure drop on the vapor mixture side. Type 2 spirals can be used in liquid-liquid systems where high flow rates on one side are offset by low flow rates on the other. Air-cooled heat exchangers. A different approach to heat transfer occurs in the fin fan or air-cooled heat exchanger. Air-cooled heat exchangers provide a structured matrix of plane or fin tubes connected to an inlet and return header as shown in picture. Air is used as the outside medium to transfer heat away from the tubes. Fans are used in a variety of arrangements to apply forced convection for heat transfer coefficients. Fans can be mounted above or below the tubes in forced draft or induced draft arrangements. Tubes can be installed vertically or horizontally. The headers on an air-cooled heat exchanger can be classified as cast box, welded box, cover plate, or manifold. Cast box and welded box types have plugs on the end plate for each tube. This design provides access for cleaning individual tubes, plugging them if a leak is found, and re-rolling to tighten tube joints. Cover plate designs provide easy access to all of the tubes. A gasket is used between the cover plate and head. The manifold type is designed for high-pressure applications. Mechanical fans use a variety of drivers. common drivers found in service with air-cooled heat exchangers include electric motor and reduction gears, steam turbine or gas engine, belt drives, and hydraulic motors. The fan blades are composed of aluminum or plastic. Aluminum blades are designed to operate in temperatures up to 300 degrees Fahrenheit or 148.88 degrees Celsius, whereas plastic blades are limited to air temperatures between 160 degrees Fahrenheit and 180 degrees Fahrenheit or 71.11 degrees Celsius, 82.22 degrees Celsius. Air-cooled heat exchangers can be found in service on air compressors, in recirculation systems, and in condensing operations. This type of heat transfer device provides a 40 degrees Fahrenheit or 4.44 degrees Celsius temperature differential between the ambient air and the exiting process fluid. Air-cooled heat exchangers have none of the problems associated with water such as fouling or corrosion. They are simple to construct and cheaper to maintain than water-cooled exchangers. They have low operating costs and superior high-temperature removal above 200 degrees Fahrenheit or 93.33 degrees Celsius. Their disadvantages are that they are limited to liquid or condensing service and have a high outlet fluid temperature and high initial cost of equipment. In addition, they are susceptible to fire or explosion in cases of loss of containment. Heat exchangers and systems. A heat exchanger system includes two or more heat exchangers working in series or parallel to raise or lower the temperature of a process stream. Heat exchanger systems may also include cooling towers, furnaces, distillation columns, reactors, hot oil or steam systems, pipes, pumps, valves, and complex process instruments. Heat transfer system. Heat exchangers are commonly used to transfer heat energy between two separate flows. In this picture, two heat exchangers are shown that heat the feed before it enters a distillation column. Feed enters the shell side of the first exchanger at 80 degrees Fahrenheit or 26.66 degrees Celsius and exits the shell at 115 degrees Fahrenheit or 46.11 degrees Celsius. Exchanger 202 has a longitudinal baffle running through the center of the shell. This partition forces the feed through a series of lower baffles to pass across the body of the heat exchanger one time before entering the upper section of the shell and moving back across the body of the exchanger and through another series of baffles before exiting through the shell outlet. The tube inlet on exchanger 202 has a feed temperature of 222 degrees Fahrenheit or 105.55 degrees Celsius as it enters the channel head and passes through the lower tube sheet and into the tubes. As the feed flows through the tubes, it transfers heat energy into the cooler shell product. Heat transfer is primarily through conduction and convection. During the heat transfer process, the temperature on the reboiler feeds drops from 222 degrees Fahrenheit to 173 degrees Fahrenheit or 105.55 degrees Celsius to 78.33 degrees Celsius. The differential temperature, delta T, is 49 and the difference in the tube inlet pressure at 135 psig and the tube outlet pressure at 130 psig is, delta P, 5. Process technicians carefully monitor these differences over extended run times. Heat exchanger 203 also has a tube inlet and a tube outlet as well as a shell inlet and outlet. Pressure and temperature are carefully monitored and tracked on checklists and statistical process control charts. On the tube side, a hot oil system is used to transfer heat energy to the shell feed. The flow rate through the shell side is controlled at 225 GPM, gallons per minute. During operation, the following variables are very important. X202. Shell inflow rate 225 GPM at 80 degrees Fahrenheit or 26.66 degrees Celsius at 135 psig. Shell outflow rate 225 GPM at 115 degrees Fahrenheit or 46.11 degrees Celsius at 131 psig. Shell delta P equals 4. Tube inflow rate 127 GPM at 222 degrees Fahrenheit or 105.55 degrees Celsius at 135 psig. Tube outflow rate 127 GPM at 173 degrees Fahrenheit or 78.33 degrees Celsius at 130 psig. Tube delta T equals 49. Pump delta P equals 95, suction equals 40 psig, discharge equals 135 psig. X203. Shell inflow rate 225 GPM at 115 degrees Fahrenheit or 46.11 degrees Celsius at 131 psig. Shell outflow rate 225 GPM at 180 degrees Fahrenheit or 82.22 degrees Celsius at 127 psig. Shell delta P equals 4. Tube inflow rate 125 GPM at 350 degrees Fahrenheit or 176.66 degrees Celsius at 35 psig. Tube outflow rate 125 GPM at 255 degrees Fahrenheit or 123.88 degrees Celsius. Tube delta T equals 95. A heat transfer system can be very complicated with modern process control instrumentation. Since a heat exchanger can explode like a bomb, proper training and care are needed during operation as well as startup and shutdown. This picture illustrates the various components found in a heat exchanger system. A flow control loop is found on the shell outlet of X203 and fails in the open position. This will prevent the feedstock from overheating and potentially rupturing the heat exchanger. Correct lineups on heat exchangers are essential, and process technicians should carefully review the standard operating procedure. Startup procedure for heat exchanger system. Prior to startup, the feed tank has been blended, sampled, and prepared for introduction into the heat transfer system for processing. 1. Notify your supervisor and all concerned about startup, downstream process technicians, I&E, engineering, maintenance, etc. 2. Ensure all safety hazards are secured, trash, locks, old permits, etc. 3. Check equipment and instrumentation, stroke control valves 0 to 100%, check lineups, etc. 4. Sample feedstock. 5. Line up feed tank to heat exchangers. Check each valve lineup. 6. Set FIC 202 to 50 GPM and put in auto. 7. Open V202B, V202F, V202G, V202H. Carefully monitor instrumentation. 8. Close V201. The feed pump has been circulating the feed and is now entirely lined up to the process. At 50 GPM. 9. Open V202C on the lower tube inlet to EX202 and open V202D on the upper tube outlet. Ensure V202E bypass is closed, call tank farm technician and ensure all valve lineups to off-specification tank are made from EX202 tube outlet to storage. 10. Line up the hot oil system to EX203, open V202K upper tube inlet and V202I lower tube outlet. Ensure V202J bypass is closed. 11. Set TIC 100 to 180 degrees Fahrenheit and put in auto. 12. Start hot oil pump. 13. Increase FIC 202 to 100 GPM and let heat transfer system line out. 14. Increase FIC 202 to 150 GPM and let heat transfer system line out. 15. Ensure flow from reboiler to EX202 to tank farm is moving and pressure instrument readings are normal. 16. Increase FIC 202 to 225 GPM and let heat transfer system line out. 17. Visually inspect all equipment, piping, and instrumentation and take initial run readings. 18. Catch sample from EX202 at V202M sample port using all safety procedures and requirements. 19. Catch sample from EX203 at V202L sample port using all safety procedures and requirements. 20. Notify all involved of any operational changes to the heat transfer system. Cooling towers. Heat exchangers and cooling towers often team up to form industrial cooling systems. The system consists of a cooling tower, heat exchanger, and pump as shown in picture. During operation, cooling water is pumped into the shell side of a heat exchanger and returned, much hotter, to the top of the cooling tower. As the hot water goes into the top of the cooling tower, it enters a water distribution header, from which it is sprayed over the internal components, filled, of the tower. As the water falls on the splash bars, cooler air contacts the water. This process removes 10 to 20% of the sensible heat that can be measured by a change in temperature. Another 80 to 90% of the heat energy is removed through evaporation. The cooled water collects in a basin at the foot of the cooling tower, where a recirculation pump sends it back to the heat exchanger. Distillation columns. Distillation columns use heat exchangers to preheat feedstock in heat exchanger, condense hot vapors in condenser, or add heat to the tower and crack or separate heavier components in kettle and thermosiphon reboilers. Condensers are typically shell and tube heat exchangers used to condense hot vapors into liquid. A condenser can be found at the top of most distillation columns. Heat exchanger symbols. Each type of heat exchanger can be represented by a symbol. This picture illustrates heat exchanger symbols. A heat exchanger allows a hot fluid to transfer heat energy in the form of heat to a cooler fluid without the two fluids physically coming into contact with each other. Heat exchangers can be categorized as pipe coil, double pipe, shell and tube, reboiler, plate and frame, air-cooled, and spiral. The shell and tube heat exchanger is the most common in the process industry. Shell and tube heat exchangers are designed to handle high flow rates in continuous operations. Reboilers are used to maintain heat balance in distillation columns. Kettle reboilers and thermosiphon reboilers are the types most often used. Condensers are typically shell and tube heat exchangers often used in distillation columns to condense hot vapors into liquid. The three methods of heat transfer are conduction, convection, and radiation. Conduction and convection are used in heat exchangers, but radiation is not used. Heat transfer occurs best when large temperature differences exist between the products, flow rates are high, and cross-sectional area is large. Laminar, that is, streamlined flow, moves through a system in layers of liquid flowing in parallel. Turbulent flow is the random movement or mixing of fluids. Once turbulent flow is initiated, molecular activity speeds up until the fluid is uniformly turbulent. Laminar flow is not conducive to heat transfer. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.